Okay, live stream should be running. That means we're almost good to go. Oh, turn this on. Yep. All right. Welcome everyone. Welcome back. That's the question from last time. So I just left this open. In case there's people who didn't attend last time but are here again this time, you can still vote. We talked about tries briefly, but I will recap that a bit before we move on. Before we start with text indexing again, are there any questions organizational side-wise? All going fine with videos, etc. so far? Okay. Well, you let me know on Campus Wire if not. That way you don't have to wait for class. Let me jump back quickly to the beginning. Just as a little recap of where we are. So we started a new unit last time, just very briefly. One that I'm very excited about because I think it goes very deep, but it does so in little small steps, each of which is quite elementary, but then if you take them together, they achieve something quite remarkable. And the first kind of these mysterious results we'll see later today. And the goal is, again, you have one big text that is static, that's fixed for us now, and you can pre-process it into a data structure, and then you ask queries. Does this pattern occur anywhere in the text? And if so, where does it occur? That will be the main task, and some variations of that are possible with similar techniques, which is why they're so popular in many applications. We started looking at this last time. So the motivation, different applications. And we talked about inverted indices. So this is in the realm where, say, we have an English text, or we have websites which tend to be natural language text. So you can usually break them up into words, and it's often sufficient to be able to search for words that occur in the text. And we identified that we could use a binary search tree for this, but there is a more suitable, slicker data structure if the keys are strings, and that's the try. And so here's an example of what a simple try looks like. I think this is where we want to start again. I briefly introduced tries last time already, and I won't get into the discussion of where the name comes from again this time. But I want to discuss the second part now a bit in more detail. So you should think of tries as trees where a node has as many children as there are symbols in the alphabet. So we often want to use these for restricted alphabets. Like in this case, the alphabet is binary. It's just the letters A and B. Now I realize that there's also this dollar symbol, and we'll talk about that in a second. But first of all, a node can have two children, one for each letter in the alphabet. It can also have just a single child as this one. And so the idea in a try always is if you follow a path from the root down the tree, like the one I sketched here, and you read the letters that you find on this path, then they give a string. And if that path leads to a leaf, then this leaf should contain exactly that string. So if you want to search for a string, say we search for, we want to know whether ABA is contained in this try, we would start at the root. The first letter is an A, so we go with the A branch. Then we look at the second letter, which is a B, so we would go the B branch. Then we find an A, so we would go the A branch. And at this point, we would like to see this dollar symbol, but there's no edge with a dollar symbol. So here we fall out of the tree, and we can report that this string does not occur in the dictionary that is represented by the try. Otherwise, there would have been an edge with that label. So this is what I tried to draw here. This was a little lightning bolt symbol, meaning that we are kind of stuck. But really what it just means, it's not in the symbol table. It's not contained in the set of strings stored represented by this try. Now, if you look at this, just this alphabet AB, if there were no dollar symbols, then we could have had this string ABA that stops in the middle of this internal node. And for various reasons, that's kind of a nuisance and inconvenient. So we will usually make this assumption for tries that the strings that we store, this set of strings, is prefix free. So what that means is no string is a strict prefix of any other string. And then you never have this situation that you have to stop in the middle of a tree. And there's two simple sufficient conditions, each of which guarantees the prefix freeness. And you can have either of the two. It depends which is convenient. If the strings are all of the same length, well, if they're the same length, neither can be a prefix of another, a strict prefix. So by strict prefix, I mean it's a prefix and it's not the same string. Duplicates are not really allowed here anyways. So if all the strings are the same length, they're prefix free. Another option, in general, if you have any set of strings, you can make it prefix free by appending an end of string character. And we'll always use this dollar symbol because it somehow became customary. Don't ask me why. At the end, everything comes down to dollars. But the only real significance is it is some symbol that doesn't occur in the alphabet. And it's convenient to have something you can type quickly. So I guess that might be the reason. And so in this case, the set of strings might originally have been AA and AAAB and ABAAB. Tough to pronounce. And then we append this dollar symbol, and then it became prefix free. Whereas previously, right, this AAA would have been a prefix of AAAB. All right. What else can we do with tries? We can insert a new symbol into the set. I thought it might be helpful to do this once on this example because many of you have never seen tries. So let's pick a string that's not already in the set. How about we do something short? BB dollar is not yet in the set. So let's try to insert this. What we do for that is we start at the root, and now we try to search for this string, which is a natural thing to check. Is it already in the dictionary? In which case we would not have to do anything. We know it's not in this case, but we still do the search. So we follow this path because the first letter of BB dollar is a B. So let's give this a name. Let's call this S. Then I can say this was the first character in S, so the character at index 0. Then I reach this node, there's another character, so I can follow this link, which is the character at index 1. And now the original string was finished here, but we added this dollar sign. So I want to add another, I want to follow another edge with a dollar sign. Now in this case, there is no such edge. But that's good because we wanted to insert. So we kind of want or expect that there is a missing edge at some stage. And so I'm just making a new one and then add the string as a new leaf. Okay. And that happened to be the second character at index 2. that's how you insert in a try. You try to follow the path as long as that works, and as soon as it stops working, you add new nodes and edges until you have inserted the new string. This could have gone on for longer. It could have been necessary to add more nodes, and then you would have created such unary paths of, we always have just one character for each edge, so we might add many more vertices. Deletion is also simple. If I wanted to delete, say, a dollar, I would start at the root. I follow a dollar. Here it is. I found it. And so deletion would just remove this and all the unary nodes above it. In this case, it's just a single edge. If we had deleted this one, we would have removed these three nodes. So the leaf and all the nodes with just a single child above it. So that's pretty much what tries can do. And next I want to see if you digested this. It's a long question, so you might need a second to read this. So the first thing to note is all strings are same size, same length. And let's say search means, is this query string contained in the set represented by the try or not? That's the simplest query, I guess. Okay, 20-ish, we're reaching number of people in the room, but there's a few at home maybe. Well, at least 3. We had 40 votes for the other question that was open for a couple of days, but I don't want to wait a couple of days. Someone pointed out that for some of the questions, I stopped them a little early, and because I'm giving you points for participation, that's kind of mean, so I try not to do it. But I also try not to show you the votes and influence in your decision to vote. So I'm not sure what to do. I could either just wait a little longer, which may be the easiest solution, but I'm such an impatient person. Or I could show you the results, and the danger is some of you might just change their mind or vote after you've seen the results. I think the second option is better, given that I'm such an impatient person. So I'll just leave the polls open so you can still vote. But yeah, you're cheating on yourself if you wait for that. It's quite interesting that there. So first of all, I was mean again. I put in a lot of different options because I thought I'll throw in anything you could potentially come up with, misguided as you might be initially, maybe. So there's lots of different options, but you see some peaks, but nothing really decisive. It's really interesting. All right, so let's discuss this a bit. I'll show you the answer here. The one that I have in mind is this one, theta of q. So roughly as long as the as the query string is. I think it's easiest to illustrate on the example again. So what we do with a query string is we traverse down a path. So remember, we use this red example here. Okay, trouble with my pen again. We use this red example to walk down the tree, and after 4 steps, which happens to be the number of characters in the query, so Q, we noticed, oh, we fell off the path. If we're lucky, we fall off the path already earlier. If we notice, say we're looking for just $1, no A's and B's in front, then right at the root we would notice there is nothing. A slightly more interesting example could be, it's a fairly full tree, but maybe something that starts with BA and then goes on for millions of characters. I would still notice after the first B and then an A isn't in the try, so I can stop early. So I can sometimes decide that something's not in the try early. To decide that it is in the try, I always have to follow the entire pattern down until I reach the leaf. And so that's what's meant in this case. I should probably narrow it down and say a successful search, because theta of Q is an upper and a lower bound. And I just convinced you that if the pattern is not in the try, you might actually stop after just 1 or 2 characters. On the other hand, we can argue this is the worst case over the data. So okay, there's a lot of slack in how you interpret the question precisely. But the usual way is you traverse down the try, and how many steps do you go down? As many as the query string is long. Okay? Now I want to take a step back here and say why this is so cool and exciting. Because the try could be really humongous. This could be an index over a huge collection of texts. Think of a search engine for the entire web. But the time to query for whether something occurs in this huge collection only depends on the length of what you query. So if you look for, you're trying to find a username and you want to see if that's unique, if no one came up with blah, 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 then you just type that in, and in the length of that string time, you know whether someone has already used that on any of the websites that there are, the trillions of websites. I think that's quite remarkable, even though there are some strings attached to it. And that brings me to this second question. So a similar setup. Again, n strings, each m characters over, say, the Latin alphabet. And now the question is, how many nodes could a try have in this situation? And by nodes, I mean the little red dots, right, from the picture. And worst case is important. So how many people did we really have last question? 22. No, that's now. Really, 44. Amazing, guys. Where do you all hide? Okay, 33. Okay, almost there, but I guess I'll just not lock the question so I can show you the results. It's a little more telling this time. Seems to be a clear peak. And this is also the correct answer. So why is it n times m? It is a little tricky, but that is effectively the worst case. What you should think about for the worst case is you branch out as early as possible in the strings, so they have all a unique prefix, and then they continue as these unary node chains. So how would this look like roughly? There's our root nodes, and we have some 26ery tree. It's not a binary tree, it's a node where every node, tree where every node has 26 children, the letters of the alphabet. And you keep doing this for a certain number of levels. Well, how many? Essentially log n levels. Oh yeah, I didn't change the screen. Thanks. And now that screen went off again. So here's my schematic picture. You have a node, then you have log n levels deep. Then you branch out to n nodes at this level, and then you go in long chains until you reach the leaves at each point. And so you have this n minus log n levels that you still go down. These are all binary, all unary nodes. So you have this m times, sorry, that's m minus log n. And each of these chains is, so you have n chains, and each of these chains has length m minus log n. And so you multiply out, the dominant term is n times m. Okay. So that's only the unary nodes in this second half of this long jellyfish or whatever, the tentacles. Okay, so again, step back from this example. Is that good or is that bad? It's terrible because that's a lot. That's a lot of space. It's a lot of nodes. And if the alphabet is big, each of these nodes has to somehow at least allow to store all these children it could have. Whereas most of these nodes, they only have a single child. So it's a huge waste of memory. If you say every node is represented with an array of 26 possible child links, then that's 26 times the length of all the strings together. So that's a huge overhead for storing this structure. So I don't think Google wants to store an index that's 26 times the size of the internet. And that's not even taking all characters into account. Remember, Unicode was more like 150,000 characters. So that's kind of a no-no. So tries have this big problem that they're space inefficient. And at least in a way here, this seems inevitable in the tree structure. Like if you have to store these strings that differ in the first few characters and then go on whatever for a long time, you have to somehow store them. So it seems you can't avoid this with this kind of tree structure. But there's a way out by modifying the data structure. And that's what people call compact tries. The bad thing in the worst case example I've shown you was that you have these long tentacles of unary nodes. What if we avoid those altogether? So whenever we have a unary node, like in this case, we remove that node and make it into one long edge. So this unary node was gone, it's consumed into one edge, and it became this edge. Okay. And you can do this further down. So here as well, long unary chain became just one edge, this one. Now, there's a few things we have to talk about. First of all, does this help? Second, how can we still search? And part of the second is, what do we write on the edges? Here we have only space for a single character, but I have BB on the path down that I contracted. And so the rule is we just use the first of these characters and we forget about the rest. They're not really forgotten because they're still stored in this leaf, so we can recover. But we have to pay attention now if we follow down a path that we compare the right characters. And that's why the compact trie additionally stores these numbers in the nodes. They tell you what index you're looking at next. So at the root, there's a 0, which means you first compare the 0 position, the 0 index of the string. And if that's a B, you go that way. Now, the next node says 2, which means you ignore what's at position 1, and you start immediately with position 2. So what that means for a search, if you were to search for BAB$, it means you start here. 0th character here is a B, so you go down here. Second character is a B, so you go down here. And so you found a leaf, and you say, yeah, the word appears. But not so fast this time. You still have to compare the string that you're searching to what you find in the leaf, because we skipped this middle character, and in general, we can skip many characters. So you still have to, at some point, check those. That's why we still keep the strings in the leaves, but the search can take shortcuts. Now back to the second point, did this help? What we achieved by removing all unary nodes is that every node that remains in the compact trie has at least 2 children. And that helps a lot because it means we never have more nodes than there are leaves. That's the same argument that we've used for binary tree counting before. Whenever you add a new binary node, or whenever you add a new node that has at least 2 children, it adds at least 1 more leaf, because it branches into 2, so you can plug it into some path. So it might take 1 leaf that was previously there and take it in one side, but then it has another side, so you have to create a new leaf whenever you add an internal node. So if you invert that argument, the number of nodes is at most the number of leaves minus 1. And that's the number of strings. So now the number of nodes is order n now, where n is the number of strings, and not n times m. Okay? We still store the strings in the leaves, so we still need this n times m space, but the constant factor is much better because the number of nodes is smaller. We just store the strings. We don't store something 20 times as big, 26 times as big. So we'll usually work with compact tries because they're much more space efficient and usually also faster, even though they're a little more complicated to do the searches. And that brings me to the end of this first part. If you want an inverted index, you can use a trie to implement that and get very efficient searches. It's relatively simple, at least conceptual. You need to implement a trie. There's tricky parts inside. How do you represent the nodes? You have basically 2 options. You can say every node stores the space for all possible child links. That is a little waste in space, but it's fast. Another option could be each node stores a little dictionary of a symbol table of child links that uses less space, but then you need the time inside the symbol table to search for the child link given a character. So that's a little more space efficient, but slightly slower. And there's nice trade-offs there. But it's overall a relatively conceptually simple data structure still. And lookup is almost as fast as it can get. You just need the time to read the pattern. But there are some downsides, and these are not really restricted to tries, but to inverted indices in general. What if you're searching for just a part of a word and you haven't spelled it out? Might be less of a problem in English, but languages like German, where you can create compound nouns that can grow arbitrarily long. If you haven't seen that, there's a nice YouTube video. Maybe I'll post this. It's probably a little tough to follow unless you speak German. But the thing is, you can make words arbitrarily long, and you can essentially tell a story in one single word. If your inverted index contains that word, that's great, but you can't search for parts of the word. And the other restriction is if you want to search something slightly more complicated, not just a single word, but a sequence, there's no easy way to do this efficiently in the trie. You need to store extra things for that. And then the second bigger disadvantage, what if there's no words to start with? If you have just some binary string that you would like to search for patterns, there's no way to build an inverted index. And similarly for these biological sequences, DNA or RNA sequences, the genome of the coronavirus, all these things, there's no word boundaries. So it seems like this doesn't work well for this. It's a little too early for our break, so I think we can introduce the star of the show today. In the next subsection, I want to show you how to overcome these weaknesses of inverted indices, that not all texts where we might want to search have these word boundaries. And so we want to have something more flexible. In a sense, we want a full text search, a full text index. Before we get back to the text indexing problem, though, I want to stress how remarkable suffix trees are. And so this is a tiny bit of a history lesson as well. And I want to illustrate it on this problem, the longest common substring problem. It's a problem where you're given a set of strings as 1 up to sk. And you're trying to find the longest substring that occurs in all of those k strings. So again, substring, not subsequence, so it must be some contiguous range. And you want to find this part of the word in all of the strings that you're given. Here's a tiny example with just 2 strings, and it's already not completely obvious at first sight. What's the longest substring they have in common? Can someone find it? Pardon? Life? Alive? So it's tricky because humans tend to recognize the parts. Well, the first is a sentence, and so we're a phrase. And you have to combine things. But yeah, alive is the longest thing they share, just because the second, there's not much left to make it longer. Now, suppose you have 100 of strings. It's not clear how to do this. And in particular, it's not clear if you can do it in essentially the same time you need to just read all these strings once. But it's possible. At least in big O of. So you're allowed to read the strings a constant number of times conceptually. But then you're supposed to tell me. And it's remarkable that this might be possible because it seems you have to. What would be a simple approach to solve the problem? You could try to go through all possible substrings of the shortest string and try to search them in all the other strings. But that's even that is quadratic in the length of the shortest string, and you haven't even searched the others. So you would need to use some string matching method for the other strings, and this would be way slower than just reading all the strings once. In the worst case, they're all the same length, all fairly long. So not so clear how to do it. But yeah, suffix trees will allow you to do this in that time, and we'll get there. It's not even that complicated. It's just building on a few really cool abstractions. To further highlight why this is even surprising for experts, so this is a quote from Dan Gusfield's book, which might be called the Bible on suffix trees, is the most complete collection of things you can do with suffix trees. And he says, he quotes Donald Knuth, which you may know as the inventor of LaTeX, not LaTeX, but tech, this typesetting system, and also the art of computer programming. And it's fair to say that he's a founding father of computer science, or theoretical computer science, and also a genius in definitely several ways. Definitely a smart person. But in 1970, he said that he conjectures there's no linear time algorithm, no algorithm with this running time for this problem, finding the longest common substring of a set of strings. And it was only 3 to 4 years later that he was disproved, that he was proven incorrect by the introduction of the suffix trees. But he didn't foresee that, and he didn't see how to do it with the suffix trees. So it's the same Knuth from the KMP algorithm. All right, I hope you're hungry for what's coming now. I tried my best to motivate this. So what is a suffix tree? The definition is just this little box, and it's all built on things you already know. The suffix tree for a text is the compact trie, so that was the version without the unary nodes, of all the suffixes of this text. So a suffix is a substring that ends at the last character. Now, for convenience, we'll always add this end of word character to our strings. So our text will have n characters, but actually the n index, the n plus first character, is always set to the $. So we will always assume this here. And then we can build this trie over all the suffixes because they're then prefix free. And yeah, that's pretty much it. And so maybe let's spend a minute on a small example. Suppose our text is this, banana. Then these are the indices. So I take all the suffixes and insert them into a trie. The easiest way to build a compact trie, if you have to manually do it, is to first build the standard trie and then compactify things. You can also do it directly, but for the manual execution of this algorithm, let's maybe not torture us too much. So we first insert banana. So we start at the root. Then we do B, A, N, banana, and the $, and then, well, I feel I don't repeat the string. So instead, I just say the starting index of that suffix. That's a little more space efficient too. I don't have to repeat the suffix all the time because it's always the suffix of the same text. So I'll instead just store the text once, and the leaf says start at 0, and you will get the string that ends here. So that was the first one. How about starting at 1 character later? That's the lovely anana. So I branch out at the root with a different letter. And that brings me to the leaf with a 1, because it started at position 1. Nana is the next one. So let's take this down here. Two. And now it gets more shorter and shorter, so it gets a little faster. Anna is already in here. I just have to add a new leaf. And that starts at 3. 4 is na. So I'm here and add a new leaf. 5 is just an A. So again, we branch out to a new leaf. And well, we could also include just the $. And so that's the standard trie. Now we want to compactify this, which means remove all the unary chains. And while we're at it, we can try to make it a little nicer. No, that's already leaf. Then here we have dollar and NA. Oh, come on. Now in the compact try, I should write the position that we check next. So if we want to do this correctly, this should be 0. This is a 1. This is a 1 as well. And this is a 1. So far we haven't skipped anything. But then here this NA becomes 1 where we skip. This goes to 5. Okay, another 2, 3. And NA dollar just goes to this straight away. This one is just one long branch, so this is actually not a 1, but leads immediately to this leaf. And on this side we have, sorry, this N, this is also not a 1, it's a 2. And then dollar to 4, and an N brings us to the 2. So you get quite a bit compacter. I tried to do this in detail for this one so that you also see the try compactification another time. I don't know how valuable it is to follow this on the slide, but if you draw the same thing a little nicer and sideways so that we can read the strings better, that's the same. Now, I will usually write on the slides the full label of the edges as they would be filled if you go to the leaf and then check, just because it's, for us, easier to work with. But what's really stored is, of course, this one, where you have only the first character each, and the internal nodes tell you what's the next character to compare. Okay, so again, the three things. This is what you often want to write on paper so that you can work with it as a human. It has the explicit strings in the leaves, and it has the full labels on the edges. We don't really store the strings in the leaves. We store just the starting index, as I showed you in the example. And we also don't really store these edge labels. Instead, we just store the first character. Okay? Now I've shown you on this example how you can construct a suffix tree. Let's see how long this takes if we follow this algorithm. We have a text with n characters, so it has n+1 suffixes because I added this $sign. And if I insert a string into a try, that essentially takes as long as the string is. So if I insert n things and they're n long, so at least the longer half are at least n half long, so you get this quadratic divided by 4 at least. It takes theta of n squared time to construct the suffix tree using this method I've just shown you. Insert each suffix one after the other. Now that's really crappy, because in quadratic time you can do a lot on strings, and in particular you can't solve this problem with longest common substrings in linear time if it already takes you quadratic time to build this suffix tree. So there's clearly something missing. The definition of the suffix tree is quite natural and easy to come up with, but the real achievement from that time is that you can construct the suffix tree in linear time. Instead of this quadratic, you can bring it down to theta n, which is, again, roughly the same as reading the text just once. In that same time, you can build this compactified version of the try, and we'll eventually see how to get there, but it will take us a few more steps in between before we can conclude that part. For now, we'll just take this as a magic black box. You can build the suffix tree in linear time, It's a little complicated, but once you have it written up, you can just reuse it many times. It's a little tricky to understand, but we'll get there. It was a theoretical breakthrough because it allowed to solve this problem. I'll show you the details in this time that Don Knuth conjectured is not possible. And the construction can be done quite efficiently in practice. So a version of this is still in use in applications like finding matches of your RNA snippets from a PCR test in the genome database. So for now, I want to take this for granted and see what can we do with it. That would be the first step as a motivation, why you want to learn, why you want to see the details of how to construct them in linear time. Before I leave you for the break, one last longish question that I maybe just leave open for the break. So lots of different statements about suffix trees. Yeah, I think I commented on all of these. Not all are correct. I wish there was a shortcut for centering the picture again, but alas. If you have any questions, let me know. I'll just spend the time. All the answers have quite a few votes, but not all are correct. 5 minutes is long if no one comes bothering me here. Also, I feel like the dog on the leash here with my mic. Oh, it's 52 for my watch. I'm already getting bored, as you could notice. So let's have a look at the Slido question. There's quite a few different answers, and you see all of them got some votes. And here's the ones that deserve to have votes. Most of you did fine. So this last part is what I just mentioned. We just treat it as a black box for now, but we'll get there. So let me briefly comment on each of these. The first one, I said, is just for convenience to represent the tries. So we do require the text to end with $, or actually we just put the $. There. The size of the suffix tree is linear in the text size because it stores a linear number of suffixes, n suffixes. And so this quadratic size was for simple tries, but for compact tries, it's linear in the number of nodes is linear in the number of strings, right? And that's n. T is not a standard trie, it is a compact trie of all the suffixes. The leaves don't really need to store a copy, so they shouldn't because it's waste of space. Instead, they store just the starting index. We can naively construct suffix trees, and then it takes quadratic time. Yeah, potentially with a compact trie constructed right away, you don't always need quadratic time, but definitely in the worst case you do. But yeah, the big magic step is you can do it in linear time. Worst case, I haven't told you how yet. And the last one is a kind of a meanie. It doesn't have n leaves as n+1 because it has n+1 suffixes once you add the $. Oh, wait. That one's not too important. We don't really need the $. Leaf for any interesting applications, but following the definitions, that's what's there. All right. So in the next subsection, I want to show you what you can do with the suffix tree, taken for granted that we can construct it efficiently in linear time in the length of the text. For that, there's one more thing we need to add that's written down here. And just as a reminder, the trie is really stored like this. It's a compact trie, so only the first label on each edge, and we store the index where the next character is compared with, etc. On the slides, I will always represent the suffix trees like this, where you see the entire string that would be on this edge if we would spell out all the characters. And then I can leave out the index in the internal nodes. A second thing that will be, it's a technical detail if you want, but it is important for the running time statements that we make, and it's also easy to achieve. I assume that all internal nodes, so every of these red guys, has a pointer to the leftmost leaf in its subtree. So in this case, it's kind of trivial, but in general, it could be that it's not so clear how far away the next leaf is. In particular, it could be in this example, there's always the the case that you have just a single edge to go to some leaf, but you don't necessarily know which edge that is. Here it always happens to be the left in the picture. But I think that is coincidence in this example and doesn't necessarily have to be like that. So it's just an assumption. Every red internal node stores one pointer, which goes to the leftmost leaf in the subtree. It's not super vital that it's the leftmost. A leaf is usually enough. If you wonder how you could construct those if they're not already there, you represent this tree somehow in memory, then you do a bottom-up traversal, and you can start from the leaves. You keep in mind in the recursion what is the leftmost leaf, and then you insert this once you go back up the tree. And you can always, when you go from two internal nodes back to the parents, you can inherit the leftmost by taking it from the child. All right, not sure if I use this very often, but T sub I is just a shortcut for this suffix starting at I. I think that should be it. Now the first application will be our good old string matching problem, the text indexing version thereof. I'd like you to think about, before I tell you how it's done, how the suffix trees help with that. So if we have the suffix tree of a text like on the left, and I want you to work on this specific example. You can make it a bit bigger if that's small. What does the suffix tree tell us about occurrences of this pattern Anna in the text? And I know this, you can read the entire text from the suffix tree and then figure it out, but that's not what I want you to do. I want you to ignore that the text is known and just work on the suffix tree and try to figure out what does the tree alone teach you about the occurrences. Is that kind of well defined? I'll leave the slide up and just have 10 votes. So I'll give you a few more minutes, seconds. In a way, this question contains all the things you've learned about tries and suffix trees. So I think it's an important one. So I'll give you a bit of time. Five votes in. If you figured it out where it occurs and you figured it out on looking at the text, try to go back and see if you can argue just on the suffix tree. Okay, 36. I think I'll show you the results and briefly on the screen as well. So we have a lot of votes for the fact that P occurs in T, and that's true. And in addition, we seem to be able to tell that it starts at index 1. So let me switch back here. It starts at index 1, but it actually also starts at index 3. Not sure if that was clear for all of you. So let me just show you how you would come up with this conclusion in the tree. Okay. So we have to find this pattern A and A in the suffix tree. It's a trie, so we do what we always do in a trie. We search by starting at the root. We follow the branch for A, N, A. And now we stop because we ran out of pattern. So what does that mean? We found some internal node here. Now, first observation, we didn't get stuck. We could follow the path. So there are ways to continue this pattern into a suffix of the text. And that means it definitely occurs somewhere in the text because the pattern is a prefix of a suffix of the text. That's nothing else than fancy words for saying it occurs in the text. Right? There's a part of the text where the pattern occurs at the beginning. Moreover, all of these suffixes are in the subtree of this very node that we stopped in the search with. All the patterns that are extending the all the suffixes that start with the pattern are below this because they all follow the same path up to this point at least. So the number of leaves below this, there's 2 leaves. That means there's 2 occurrences of the pattern in the text. And if you look at the index in the leaf, that's the index where the pattern occurs. And so that's exactly the indices 1 and 3 where we find Anna in the text banana ban. Okay? Good. So if you follow this, then the algorithm on the next slide will be quite natural. And that's our first application of suffix trees, our good old friend string matching. Just that in this case, we tend to think of it that the text is static and we search several times, but we don't have to. So one way to do string matching is construct the suffix tree for t, and then exploit this fact that I mentioned before. P occurs in the text exactly if and only if P is a prefix of a suffix. And so here's the algorithm spelled out again that we are following to find these occurrences. We search the pattern in the trie by following it down from the root. And then there's really 3 different options in theory, in principle, that can happen. If we ever get stuck, so there's 2 options, 2 subcases if you want. We are at an internal node and the next character of the pattern, there's no edge from this node that we can follow. Then we're stuck at an internal node. We can also get stuck inside an edge. Remember, so here we have several characters on an edge. Maybe we try to find BAA and not BAN. Then we would fall out of the edge with the 3rd character. Now remember, we would normally not discover this until we jump to the leftmost leaf and then start comparing from there. But let's ignore that fact and abstract from that here and assume we have all the characters on the edges present. So that's 2 ways how we can get stuck. If we ever do get stuck, that means the pattern doesn't occur in the text because there was no single suffix that started like this. So I can't continue following this path. The other option is we run out of pattern as in the previous example. So we could read the entire pattern and we end at some point in the trie. And that can be either at an internal node, like in the previous example, or it could be in the middle of an edge. But both are really the same in this case. If you check the characters inside the edge, then the pattern occurs at all the indices of the leaves in the subtree of where you stopped. In theory, there's also a 3rd case. We could run out of tree, so we could traverse and traverse with our pattern, and then we reach a leaf, and the pattern would like to keep going. This can't really happen in our scenario because we added this $sign. So if $, doesn't occur in the pattern and we kind of enforce that, then we can never reach a leaf. because the leaves always have as last character the $sign, and that's forbidden in the pattern. So that case doesn't occur. If it would occur, we could still handle it by going to the leaf that we reach and check if we find P there. So in total, the algorithm follows the path of the pattern, and after at most length of P steps, you found one of the two cases, the first or the second. And so you can either say there isn't a match in the text, or you can report at least one occurrence in constant time by following the next leftmost leaf pointer. That was the green one before. So that's how you can find a first match in the length of the pattern time. If you want to report all matches, you can also do this, but you can't keep it in that time because the pattern in the worst case could occur at every position in the text. So even to just produce the output, you need more time. But how you would do it is if you wanted to report all occurrences of an A in the text, you would go from the root to A, and then you would just walk through the entire subtree and report all the leaves you found. That's linear in the number of occurrences. So you can report all occurrences in time length of the pattern plus number of occurrences. And that's, again, best possible. You need to read at least the pattern, and you need to write out all the positions where it occurs if that's the goal. So you can't really beat that. OK, that was the first big application of suffix trees for string matching. I have some examples that hit all the possible cases. What do you feel like? Shall we go through those, or is it clear enough without the examples? Who wants to see examples? Who does not want to see examples? OK, so I'll go for the middle and go through all of them, but quickly. I'll try. Let's do this one. So ANN, bloop, I fall out of the tree. So that's a case of we get stuck at an internal node. OK, doesn't occur. Let's see if I run out of colors. BAA. So BA, and then bloop, I fall out of the edge inside the edge. So that's this case. Doesn't occur, right? I would have had to match the N. Anna was the example from before, so maybe we can skip that one, right? That was ANA. So we end at an internal node, and then we can use the green pointer to jump and report 3 as one match. BA. OK, yellow was maybe a mistake. We traverse the same edge as with the blue, but then we stop in the middle of the edge. So here it's not a mismatch, but it's this case. And so the occurrences are everything below here. So we just follow the rest of this edge. And from there on, it's the same as the orange case. And now the last one might be more interesting. That's my color for corrections. So Briar. That's a tricky one. We would normally say after this B, we fall out of the tree because there's no R. So what this shows is if you have the compact trie, you would actually just look at the first character, and that matches. So you would jump over these, and then A matches again. So you would jump down to this leaf. And so once you reach that leaf, you know the text that's stored there is actually the entire text here. And so you would align this like this and would notice that there's a mismatch at the second character. Okay, so that's in a sense the same as the blue one. So if you go by the proper implementation as compact try, then you wouldn't really check these other characters until you reach the leaf. And so that's something to keep in mind. For the conceptual algorithms on the slides, I'll assume we have the full labels on the edges. And you can always handle these two cases in an implementation separately. So that you fall out of the edge, or that you run all the way to a leaf but actually have jumped over mismatches. Okay? Other questions on the examples? I have more applications. And this one is slightly related to the motivating question, but we're one step ahead, one step away from that one. So in this case, we asked for the longest repeated substring of a single text. So we have a text, and we would like to find two indices, I and j, so that if you start reading at I and j, you see the same substring. So maybe for illustration, a little picture, this is your text. You're trying to find positions I and j. And when you read here, you read the same string up to a certain point. So there's a length L, so that this and this is the same string. And you try to find the longest L so that you find these positions I and j. This is indeed something we'll essentially come back to in disguise. It'll be a subproblem for something later in compression, but we don't need to worry about that for now. It's also just an interesting question. I mean, a curious question. You have a text. What's the longest thing that occurs at least twice as a literal copy? Again, if you think from first principles, it looks like one of these problems where you have to go through all substrings, and so it smells quadratic. But you can actually do it with suffix trees, again, in linear time. It's a lovely thing to ponder about if we have more time. But I think for this one, I'll just have to give you the key insight away. The trick here is that if there is some repeated string in the text, like in this one, that means there's a suffix starting at I and a suffix starting at j, which both start with the same string, namely this green part. What does that mean in the suffix tree? Well, there's a suffix there's the two suffixes that are stored in the trie. And if they start with the same string, they share a path from the root up to a certain point, and then they diverge. So there must be a shared path in the suffix tree. And if it's a longest shared path where they diverge, it actually ends in an internal node. So let's see on an example what that could look like. In this short example, here are two suffixes, and they have a longest common prefix of just the single a. Well, if you try to find a bigger example, things get a bit unwieldy, so bear with me that the example's a bit small. But because those two have the longest shared prefix a, they share a path up to this point and then they branch off. So there must be an internal node at this position that we reach with the path a. And of course, if we go down to a, here is this internal node. It's not so surprising here, but in general, it could be further down. It could be a long shared path. And indeed, there are other examples here of longer shared paths. We'll come back to that in a second. Now, how do we find the longest repeated substring? First observation, any internal node corresponds to some repeated substring because the path from the root lies on at least 2 paths to a leaf. So if we want the longest, we want the one that has the longest path from the root. Okay, so in other words, that's the longest common prefix of any 2 suffixes. And this brings us to what is called the string depth of a node. That's just the length of the path from the root. So maybe let's annotate the tree with these string depths. The root is at 0. Then here, this one has just a, so it's at 1. an is 2, a and a is 3. This one has 3. It's just a single edge, but 3 characters. And so that's it. So we can do this in a bottom-up traversal again. Sorry, in a top-down traversal, in a depth-first search from the root. We start with the root at 0, and then indeed the compact trie, in a sense, already stores the string depth because it stores the index that we compare next. That's exactly the string depth. So we don't even have to really compute this. If you represent the suffix tree as on the slide, it seems like this is another step. And then the second is you just look for a node with maximal string depth. So in this case, we have 2 examples. So there's 2 longest repeated substrings, ban and Anna. Okay. And so how much time does this take in total? We need to construct the suffix tree. It takes linear time using the magic black box algorithm. We need to find the string depths of all the nodes, but they're actually already there. And we need to find a node with a maximal string depth, and that can be done by just walking through the tree once and keeping track of the deepest. So that's linear time overall. Okay. That's pretty cool and is already quite close to this longest common substring between different strings. But there's one thing that stands in our way to solving this motivating problem. The motivating problem, where you find the longest common substring, talks about several texts. And so far, our suffix tree was always just for a single text, for a single string. There's a way, though, fairly conceptually easy, to get from a suffix tree for one text to a suffix trees for several texts. And that's called the generalized suffix tree. So that's just the observation. We would like to close the loop to this motivational problem. So we need something that works for several texts. What does not seem to help is to build the suffix tree of all the texts individually. So you could build one suffix tree each, but I don't know of a way to make use of that really. Because what we need is the information combined of the texts. We need to find the things that are repeated between texts. So I can find all the repetitions inside a single text with this, but that's not really, that's like a wrong question. So instead, what we'll do is we'll force all the texts into one big text using a little hack, if you want. We create an artificial new text where we concatenate all the strings that we have, but we separate them with new dollar signs, which are different for each text. So we create k new characters so that this $I tells you which of the substrings ends there. So at the expense of k new end of word symbols, we can construct a single text and can construct the single suffix tree for this concatenation of texts. And that's it. That's called the generalized suffix tree. There's a slight simplification you can make if you have an edge in this generalized suffix tree that has some $j, you know that it will always lead to a leaf because these dollars are unique. They occur at only one place, so there's no way how they can be shared with different positions. So they will always lead to leaves. And so we will have for every text j and every position in the text j I, we will have one suffix. So that's the suffix starting at position I of text j, denoted like this. And we will have a leaf for each of these pairs, right? For each text and each position, we will have one leaf. And you can figure out that this is a certain starting position in this text t. You just sum up the lengths of all the previous texts and add I. So there's a way to translate between the indices in t and these pairs, which text and which index inside. That's something we'll just take for granted. Okay, a short one to wake you up. That one has nothing to do with suffix trees yet. Just reminding you of the definition of the problem before I'll show you how this works with suffix trees. I want to show you the algorithm before we run out of time, so I'll show the results, and BCA is the right answer, right? That occurs here and here and here. And here it occurs actually twice, so you can, okay, I didn't show it. In this first string, even occurs twice, but that doesn't hurt. So we hope to find this BCA. I'll show you an example for the generalized suffix tree for these three strings on the next slide. I want to briefly first highlight what we need to do. So by building the generalized suffix tree, we basically have the information that's needed there. There's only one piece missing. Any path from the root to an internal node corresponds to some repeated string. But that's not good enough. I don't know where this repeated string is. It could be just in two texts, not all, or it could be two occurrences within one text. So I need one second piece of information. And so I annotate all the nodes in this generalized suffix tree by all the substrings that have some leaf from this substring below it. We can do this bottom up by, for the leaves, just take the single string they correspond to, and when you go from children back to parent, you just take the union of all the substrings. That's how you can compute this in linear time. Then we also compute the string depths as before. And finally, we report the path to the deepest node in terms of string depth that is annotated with all the strings. So there is a leaf for all the strings below this node. And that means it's a shared substring that occurs in all the strings. Okay. And here, what I noted here is the total length of all the strings. They don't necessarily have the same length, but you just sum up all their lengths. And that's roughly the time you need to build the suffix tree as well. And all the rest also runs in this same time. So here's the example how this looks like for the three texts from the question. So here are these three. You concatenate them with the dollars in between in this order left to right. And you build the suffix tree for them. And I guess you'll have to take my word for it for this one, that this is what comes out of it. And these green numbers here, these are sets of numbers, 1, 2, or 3, and there can be one missing. And you see how this is formed. You have a $2 here, so this is a leaf that corresponds to the second, respectively the first text. So you have a leaf for text 1 and text 2 below 4, but none for below this node, but none for text 3. And you do this for all the nodes. Here you have something from 3 and 2, so that's why there's 2 and 3. If you go to this node, you take the union of these, and you don't even need the other leaves to see that there's something from all 3 strings below it. So that means the path from the root to this node occurs in all 3 strings. That's brilliant, but it's not the longest such repeated one. Indeed, we find here is one that has string depth 3, and that's the biggest string depth we find in this example where all 3 are present. And the path from the root to this node is BCA. That's our longest repeated substring that you also found. Okay. So it's only a small step from a suffix tree from one text to one for several texts. And with that little trick of adding these dollars in between, you can use the construction as a black box for one text by creating the concatenation. And thereby solve this really challenging problem that at first seems to require quadratic time or more. Cool. That's the end of the first round of applications. There's more to come, but that we'll reserve for next week.